Okay, I'll go ahead and get started. So today we want to talk about logistic regression. And to start off, I want to review regular linear regression, least squares linear regression, or what we call the general linear model. And so in this case, in this analysis, we have a dependent variable or outcome that's continuous, and it's assumed to be normally distributed, although that doesn't have to be precisely the case. You can violate that assumption quite a bit and still be okay. But in linear regression, the regression coefficients are the change in y for every unit change in the independent variables, whether you have just one or whether you have a multivariable equation where you have multiple independent variables. And in linear regression, not the only one, but one of the really important statistics to calculate as far as how good your model is the R-squared value, which is the proportion of variance in your outcome accounted for by the independent variable or variables as the case may be. So in contrast to this, binary logistic regression is part of what we call the generalized linear model. And in binary logistic regression, as that indicates, the outcome is dichotomous. And so we would have things like yes or no, dead or alive, remission, not remission, whatever the outcome might be. And so in this case, we can compute the odds of the outcome, which is just the probability of the outcome divided by 1 minus the probability of the outcome. And so in this case, our equation is going to be the log of the odds equal to some combination of independent variables or predictors of the log odds. And so the independent variables, the x in this case is however many we have, whether it's one or several. And the regression coefficients, the betas or the b's, however you want to do those, is the change in the log odds of an event with 1 unit change in x or in the independent variables. And this can be either increasing or decreasing, but we still have a linear equation. And so as we mentioned in the linear regression, we're assuming that our outcome is normally distributed or nearly so. In logistic regression, we have a different distribution, the logistic regression curve here. And you might say, well, that doesn't look very linear to me. Well, it actually is if you consider the sort of the middle of the curve right through here. The problem is when you get to the extremes is when the logistic regression sort of breaks down. In other words, if we have an event that we're interested in, an outcome that we're interested in that occurs almost all the time, then we're up here in this range of the curve, and our model is probably going to have break down. Similarly, if we're in the lower end of the curve where we have a really rare event or rare outcome, its probability near 0, then we're also not going to have probably a really great model, or there's going to be some issues with the logistic model. So the regression coefficient is similar to the linear regression, is a slope coefficient. And so it's, as I mentioned, it's the rate of change in the log odds of the event as independent variable changes 1 unit. And so once we solve our regression equation, or we solve for the regression coefficients, the betas, then we can calculate the probability of the event dependent on whatever our independent variable or variables are. And so that's a fairly straightforward equation where the probability of the outcome as a function of the independent variables is just the exponentiated regression equation divided by 1 plus the exponentiated regression equation. So for any say change, if say for example our independent variables age, then we can calculate a probability of the outcome for any given value of age using this equation. So the sign of the regression coefficient, the beta, determines whether the log odds is increasing or decreasing for every 1 unit increase. So always remember that it's always for the independent variable, we're always talking about a 1 unit or whatever units we have increase. And then the beta, the sign of the beta determines whether the log odds is increasing or decreasing. And so if our regression coefficient is positive, then we have an increase in the log odds of our outcome for every 1 unit increase in our independent variable. And if it's the regression coefficient is negative, then we have a decrease in the log odds for every 1 unit increase in the independent variables. Now, if the regression coefficient is 0, then we have no linear relationship between the log odds and the independent variable. And so obviously, as you probably as you would guess or know, we're going to determine whether the beta coefficient is equal to 0 statistically. In other words, we're going to calculate a p-value for the regression coefficient and determine whether it's statistically 0 or different from 0. The important thing to remember in logistic regression is that if we exponentiate the regression coefficient, and remember that is a log odds, then we have the odds ratio, which is probably everyone's familiar with, or most people are familiar with an odds ratio. But we get the odds ratio by exponentiating the regression coefficients. So I have an example here, really simple example, and you can sort of see where this is going because I made up the data, but I have age and coronary heart disease. And so we're going to look at coronary heart disease, yes or no, as a function of age. And so the way that I've coded this and the way that you would typically code a binary outcome is either 1 or 0, where 1 is the outcome, the particular outcome that you're interested in. So in this case, 1 means yes for coronary disease and 0 means no. And so that's typically the way that you would code your binary outcome with a 1 or a 0. So here's my regression equation. And so you can see that CVD as a function of age. The regression coefficient is almost 0.1. The constant, or the beta sub 0, is minus 5.2. And so you can see that my regression coefficient for age is statistically significant. So for the log of the odds, that means it's different from 0. And you can see by the 95% confidence interval that that's the case, that it does not include 0. And so we have a statistically significant log odds for age as it predicts cardiovascular disease. And so then using our formula that we saw earlier, we can get a probability for any given age by exponentiating the regression coefficient. You can see there minus 5.2 plus 0.1 times the age. And then we divide that by 1 plus the exponentiated regression equation. And then we will get the probability of cardiovascular disease at a given age. So whatever age we want to calculate. And so I have the same regression here, except now I've asked for the odds ratio instead of the log odds. And so now, if I take the exponentiated coefficient that we saw in the previous slide for age, I get an odds ratio of 1.1. And consequently, you can see that the 95% confidence interval for the odds ratio, now we're not talking about a confidence interval that doesn't include 0, but that doesn't include 1. Because if we have an odds ratio of 1, that means there's no difference between treatment groups, or there's no difference in age as it relates to, in this case, cardiovascular disease. And so you can see that in this case, my 95% confidence interval does not include 1. So the way that I interpret this then is for every 1 year increase in age, the odds of cardiovascular disease increases by a factor of 1.1. Or another way of saying that is there's a 10% increase in the odds of cardiovascular disease for every 1 year increase in age. And so where do I get the 10%? Well, you can see on the odds ratio that if we take the odds ratio minus 1, then we get the is interpreted as a percent percent change, a percent increase in this case. Okay, so if we have just say 2 groups, in this case I have an intervention and control groups, then we construct a 2-by-2 table of events by our groups. And so I have 46 events in the intervention group and 37 in the control group, and I've made this come out to have 100 in each group to make it easy for the calculations here. But I can calculate the odds ratio from this table by taking the odds for the intervention group, the odds of the event, divided by 1 minus the odds of the event, and then I divide that by the odds of the event in the control group, divided by 1 minus the odds in the control group. And if I carry out the math here, I get an odds ratio of 1.45, which we can also get this odds ratio by a simple mathematical reduction of the formula above by taking the ratio of the cross products. So I can get the same odds ratio if I take 46 times 63 and divide that by 37 times 54, and I get the same odds ratio, 1.45. And so how do I interpret this? It means that the event, whatever that might be, is nearly 1.5 times more likely to occur in the intervention group. And then if I want to know if this is statistically significant, I can get this from the chi-square of the 2-by-2 table here, which tells me whether the odds ratio is different from 1, or I can compute the 95% confidence interval and see if it includes or doesn't include 1. In this case, it probably won't include 1. Or, as I mentioned before, you can also say that there's a 45% increase in the odds of the event in the intervention group than there is in the control group. We can, of course, then do multivariable logistic regression where we have more than one independent variable. And so these independent variables can be of any type. They can be dichotomous, they can be ordinal, nominal, continuous. And we interpret the regression coefficients, the betas or the b's, in the same way. It's the increase in log odds for 1 unit increase in the independent variable or the x's, with all other x's held constant. Or another way of saying that is it's a measure of association between the independent variable and the log odds adjusted for all other variables in the model. And so I want to show an example here of results from a study we did some years ago, where we looked at PCI patients, per cutaneous intervention patients, percutaneous coronary intervention patients, and their 30-day readmissions. And so in this case, we just did whether they were readmitted within 30 days of discharge, yes or no. And so these are the odds ratios that we get with their 95% confidence intervals. And so, for example, age, which I've done in 10 rather than in 1 year units, I've done it in 10-year units. So the odds ratio here is interpreted as the odds of being readmitted within 30 days increases at a rate of 1.25 for every 10 years increase in age. Or, as I mentioned before, I can also say that for every 10-year increase in age, the odds of 30-day readmission increases by 25%. And then you can see the other odds ratios I have here that you interpret in the same way, except you note for race now, where I have 3 categories, not just 2, I have to indicate one of those categories as the reference category. And so in this case, I've indicate race, the white race is the reference category, and black and other. Then the odds ratios are in relationship to the reference group, in this case, the white race. So the way that we would interpret this is that for blacks, the odds of being readmitted within 30 days is 30% greater than it is for whites. We have a few odds ratios that are now less than 1. And so our interpretation of that is a decrease, because if we have an odds ratio that's less than 1, that means that our regression coefficient, our log odds, was negative. So for example, for those who have elective procedures, their odds of being readmitted within 30 days is 41% less than that for non-elective procedures. So in this case, you're just subtracting the odds ratios from 1 to get the percentage. And so then you could interpret the others in the same way. So odds ratio less than 1 means that we have, for an increase in the independent variable, we have a decrease in the odds of the outcome. At the bottom of the table, you see that I have something called a C index, which is equal to 0.76. And so, as you recall, we mentioned that for linear regression, one of our key statistics to tell us how good the model was, or how good our prediction was of our outcome, the C index is one of the major statistics to determine how well our logistic regression is doing, or how well the model's doing. And so when we evaluate logistic regression models, the primary one that you often see, although sometimes people don't include it in their logistic regression, is the C index, which is an index or a measure of discrimination. And it turns out that the C index is also equal to the area under an ROC curve. But the index can range, or ranges from 0.5 to 1. If we have a C index of 0.5, then that means there's no discrimination with respect to our model or our independent variable or variables, as the case may be. In other words, the outcome is just a coin toss as to which group or we are predicting. If we have an index that's usually greater than 0.8, then we're really happy, because that's really good discrimination. Sometimes you see discrimination indices, or the C index of 0.6, between 6.6 and 0.7. And I've seen articles where they say, well, that's really good, discrimination index, but it's really not. That's probably at best mediocre. The other evaluation statistic for logistic regression models is what we call calibration. And this means, do the predicted probabilities from the model equal the observed probabilities? And so the way that we look at this, or the way we do a check on this, which you often don't see as much in the literature, is that we do a plot of observed probabilities with predicted probabilities. And so in this case, what we hope for is that we get, when we do this plot, we get a slope of 1, which means that we have a 1-to-1 correspondence between the observed probabilities and the predicted probabilities. And so going back to the study on 30-day readmissions, this is one way of doing our calibration plot, where we usually take deciles, but in this case, I just took quintiles of predicted readmission, calculated the probabilities, and then plotted those with the observed proportion readmitted. And so you can see that this is at least in the right direction. It's probably not exactly linear. It looks a little more curvilinear, but anyway, the low probabilities, observed low probabilities, are associated with low predicted probabilities grouped in quintiles. And as the observed probabilities increase, so do the predicted probabilities represented in quintile 5. Another way that you see this done is actually to do a plot where we have our ideal calibration line, and then we plot the calibration slope that we get from our calibration line that we get from our model. And so we're hoping that the slope of our calibration line is close to 1. And so in this case, you can see that we have pretty good calibration there, that the slope is 0.97. So those two measures, discrimination and calibration, is what we want to look at to evaluate how good our logistic regression model is. Okay, so what I'd like to do is take some time here to go through a publication that used logistic regression. It was published a number of years ago, in 2018. And basically, this is looking at mitral valve repair or medical treatment for secondary mitral regurgitation. And so I've just kind of pull out here so you can see it, because it's probably hard to see the article itself. Their design here is a random trial. So they randomly assigned patients who had severe mitral regurgitation to receive mitral valve repair plus medical therapy, or just medical therapy alone. So that's our basic design as a randomized clinical trial. And so they recruited patients for almost 4 years, 2013 to 2017, and they recruited patients from 37 different centers or institutions in France. So this is when you read an article, you want to start to pay attention to this. Where are the patients coming from? The issue here is not that they're coming from France, but if they're coming from 37 different institutions. So that's a potential problem and an issue that we may need to address in doing our analysis. Now, they don't do it here in this analysis, but if you do have data coming from different centers, medical centers or medical institutions, that may be something that you need to account for in the analysis. So their primary efficacy outcome is a composite of death from any cause or an unplanned hospitalization for heart failure at 12 months after randomization. And so in their statistical analysis section here, we have two things that we need to note. One is their power analysis, or determining how many patients they're going to need. And so they cite a study where the outcome, in other words, hospitalization for heart failure or death from any cause, was as high as 50%. And then there was a previous study that indicated that the rate was only 33%. So what they did is they powered their study on a 17% difference between mitral valve repair and medical treatment. And they did this just by doing the chi-square test that we showed earlier, and then they included a 10% loss to follow up. And so their statistical analysis is just what's called an unconditional logistic regression. So we're basically just looking at the outcome as a function of the treatment groups. So in other words, there's no other variables included in our model. Now, if this had not been a randomized trial, if it had been an observational study, then we would have needed to do what we call, obviously, a conditional logistic regression, where we have included other covariates that may influence the outcome, which typically are things like age, sex, race, if there's comorbid, if they have a history of different comorbidities, they would be included. But since this is a randomized trial, then we can assume that the randomization has washed out any differences between the two groups with respect to other potential confounding variables, and we can just do the look at the outcome as a function of the treatment groups. And then in addition to doing the logistic regression, they do a survival analysis. So the difference here is that they're looking at the outcome, death or hospitalization for heart failure within 12 months is just yes or no. But then they're also going to do an analysis where they actually look at the time to hospitalization, which is the Kaplan-Meier analysis. So we're going to focus primarily on the logistic regression model here. So a couple of things that are mentioned in the article. I won't go into any detail here, but they did some subgroup analyses of the primary outcome. And typically, even though it's a randomized trial and there should be no differences where related to subgroups, a lot of studies do it anyway. And then they mentioned that there's a substantial amount of missing data for echocardiography for functional status and quality of life, which they also obtained, but they don't report the results of these as far as statistical tests of hypotheses. And then that their primary analysis here, which it always needs to be in a trial, randomized or not, is what we call intention to treat. And so you can see that it's possible, like especially like in this case, that a person might be randomized to receive medical treatment alone, but their physician determines, well, they also need to get a mitral valve repair. And so they would be what's called a crossover. But in the primary analysis, you would count this person as a medical treatment only. But then patients, there's enough crossovers, then patient or investigator usually do what's called a protocol. That is what they actually ended up receiving. So looking at our outcomes, one thing I mentioned, they have about their power analysis indicated they needed 144 patients in each group for a 17% difference in the outcome. And so then when you add in the loss to follow-up, I think they had like 150 some in each group. It wasn't quite equal. 152 in the mitral valve repair and 155 in medical therapy alone. But anyway, looking at their outcomes, which is death or heart failure hospitalization within 12 months, you find that there were 83 in the mitral valve repair group and 78 in the medical therapy group. And so when they calculate the odds ratio, they get an odds ratio of 1.16, which is not statistically significant. Now, a few things to note here. First of all, which I'll talk about later in their conclusions, is that a 17% difference is really a big difference. So it's very possible here that it is true that they're underpowered to find a smaller difference, but also with only a couple hundred patients or 300 in doing this kind of analysis, you probably should have a lot more than several hundred patients and probably need patient numbering in the thousands. But anyway, you notice that the odds ratios is greater than 1.16. So what this means is that the outcome, death or hospitalization for heart failure, there's a greater odds of that in the mitral valve repair group than there is in the medical therapy group. In other words, the odds of the outcome in the mitral valve repair group increases by a factor of over 1.1, almost 1.2. So this is actually not a real great finding as far as their hypothesis is concerned, because they would have expected the odds ratio or hoped the odds ratio would be less than 1, which would indicate that the odds of the outcome in the repair group was less than that in the medical therapy group. And so here's a table of their results. Might be hard to read that, but basically that's showing the percentage in each group, and then the odds ratio of 1.16, and the p-value associated with that is 0.5. So obviously not statistically significant. And then the figure here is their Kaplan-Meier analysis, where now they've looked at the time for each patient to the event, not just yes or no, whether they had an event. And so that you can see that even from the Kaplan-Meier, even though there's not a statistically significant difference between the Kaplan-Meier curves, you can see that the control group is kind of doing better than the intervention group. And so in their conclusions, they make some statements here as far as their limitations are concerned. And one is that they had 14 patients in the intervention group that actually didn't get the procedure. So that's kind of a big issue, at least in my mind it is. And then they state that they did not have power to detect a smaller difference, but their results didn't suggest a trend in favor of repair anyway. And so they come up with this rather bland conclusion to a not so great study as far as the outcome is concerned, that at 12 months, there was no difference between the intervention and control group with respect to the outcome of death or hospitalization within 12 months. So this is, you can see how logistic regression is used in an actual study. This one didn't turn out, I'm sure, like they had hoped, but it's a negative study that got published anyway. So perhaps the area was of great interest to readers. Okay, so I want to kind of finish up talking about some issues related to logistic regression that you need to be tuned to. And one is getting extreme values. Extreme values in terms of the odds ratio or the confidence intervals. And so this is going back to our 30-day hospitalization study, where we've added some different variables. And so you can see here, I've highlighted several where we have a potential problem. And so one of them was, one of the things was to look at the intervention in year 1 and then look at it again in year 2. In year 2, you can see that the odds ratio is nearly 0, and that the lower 95% bound of the lower bound of the 95% confidence interval is virtually 0. Then also, so that means that we have some issue with that. That is, the odds ratio is a little bit suspect here. And then you can see that for females, we have a huge odds ratios of nearly 23, and the upper bound is almost 300. And so even though the p-value tells us that that's significant, you can see that the wide confidence interval tells us that we may have an issue here with a lot of females experiencing 30-day rehospitalization compared to males. And then for the other race, Medicaid and insurance, the other insurance categories of self-pay and other insurance, you can see that we have odds ratios that are virtually 0, as well as confidence intervals that are virtually 0. And so it's these kind of things, if you encounter these in your analysis, you need to be very suspect that these are probably not really reliable, and that you perhaps need to adjust the variables in your regression equation to take care of this. In other words, what these are saying, like for females, we're probably up the upper end of the logistic curve, where many more females than males are experiencing 30-day readmission. And then the insurance categories of Medicaid, self-pay, and other insurance were very close to the zero end. So we have probably not very stable estimates of the odds ratio. Okay, so some other issues that we need to talk about are we can categorize continuous variables that aid interpretation, but know that when you do that, it decreases power. And so one of the primary ones that falls in this category is BMI, body mass index, because often this is a continuous variable, but you often see it categorized into underweight, normal weight, overweight, obese, and morbidly obese for the analysis, which makes it easier to kind of interpret, but when you do that, you're going to lose power in your analysis. Also, if the relationship between the outcome and the continuous variables you have in your equation is nonlinear, then you can't really interpret the odds ratios as you would if it's because it's a linear. The logistic is a linear function. And then also you need to, and especially if you're reading literature, really pay attention to the model discrimination and calibration indices. And even though if you get a model that's statistically significant, but the index is less than 0.7, then you have to have a suspicion that your model is maybe no better than chance in predicting the outcome. Okay, so I want to talk here at the sort of end of the presentation about the situation where we have more than two categories in logistic regression. So binary logistic regression is really pretty straightforward to do and to interpret, but we can also have more than two categories. And so there's two types here. One we call ordinal logistic regression. And by this, we mean that the categories that we have are ordered in some way. Now, they're not numerical in the sense that they're continuous, so that there's an equal distance between each measurement, like the distance between 1 inch and 2 inches is the same as the distance between 9 inches and 10 inches. And an example of this would be cancer stages. So we might have 4 stages that are obviously ordinal, that the higher the stage, the worse the cancer, but the distances between the two are not particularly defined numerically. They might be defined by imaging, but they're not numerically defined. And then the other type is what we call multinomial logistic regression, where our categories are unordered. In other words, we have different categories, but they're not ordered in the sense of one being higher or lower than the other. And so the example I have here is insurance categories, where we have private, Medicare, Medicaid, self-pay, and uninsured. So they're different categories, but there's no particular ordering that we would assign to these. So I want to go over a couple examples, because interpretation where you have more than two categories is a little more trickier. So I want to use an example from our hypertrophic cardiomyopathy study, where one of the variables that we obtained was from imaging was morphology of the heart. And so there's different categories of morphology, basal, septal, and reverse curvature being the two primary ones. And there were several others, but I just grouped them together in others because there wasn't enough in each category for a meaningful analysis. But these are obviously unordered categories. And so what I want to look at, or what I want to do, is a multinomial logistic regression for the three categories here of septal, reverse curvature, and other, and look at that as a function of age, sex, and body mass index. And so here is my analysis. And so in this case, where you have more than two categories, one is going to become the base category, or the reference category. In binary logistic regression, our reference category was always the category that we coded as 0. But so here in this case, the basal septal is my base outcome, and then I have log odds for the reverse category and the other categories. And so here what I've highlighted are for age and BMI in the reverse curvature category. They appear to be statistically significant. And so what I've highlighted here what the coefficients are. Remember, these are the log odds. So what I can do then is I can exponentiate the log odds to get the odds ratio. And so if I exponentiate minus 0.035, I get an odds ratio of 0.965, and exponentiating minus 0.033, I get an odds ratio of 0.968. So they're essentially the same. Basically, I have an odds ratios of 0.97. So what this means in terms of interpretation is that adjusted for BMI and gender, for every 1 year increase in age, the odds of being in the reverse curvature category decreases by about 3%. And then the same thing is true for BMI. For every unit increase in BMI, the odds of being in the reverse category decrease by about 3%. And then you can see that for the other morphology category, that none of those are significant, although age is fairly close, and it's in the same direction as for the reverse morphology group. So obviously age is probably the primary factor here. But anyway, so you interpret this in terms of the regression coefficients being the log odds, and you can change, compute the odds ratios for those, and that's always in comparison to your base outcome or your reference category. So what this means then, as I've mentioned before, is for every year increase in age, the odds of reverse curvature are reduced by 3% compared to the basal septal category. And for every kilogram per meter squared increase in BMI, we have the same conclusion that the odds are reduced, of reverse curvature are reduced by 3%. So that's an example of a multinomial regression where we have three different categories. So then I want to do another one where I'm looking at ordered categories. And so in this case, I'm going to do ordered logistic regression. And my outcomes here are infant weight, which is categorized as less than 750 grams, 750 grams to 1,000, and then greater than 1,000 grams for the birth weight. So you can see here that my, although they don't show it in this particular software, the comparison group is the greater than 1,000 grams group. And so here, and I've asked for the odds ratios instead of the regression coefficients or the log odds. And so you can see that for the middle category, the 750 to 1,000 grams, that for IL-6, which these IL-4, 6, and 8 are inflammation markers. And so for IL-6, you can see that there's a significant decrease in the odds of being in the middle group, the 750 to 1,000 group, by a factor of 2%. For the IL-8, there's an increase because the odds ratio is greater than 1, although not much greater. Because this is the odds ratios are so close to 1, we might in this case want to do more than just look at just a 1 unit increase in our independent variables. So what we can do is we can rescale our odds ratios. And so now I have my table here in terms of the regression coefficients, in other words, the log odds. And so I can then rescale these. So what I'm going to do is instead of 1 unit, I'm going to look at 50 units. And the units here are PG per milliliter for all, I think generally called cytokines. But anyway, if I multiply the coefficient, the regression coefficient by 50, then I can, I get a regression coefficients or a log odds. It's for an increase in 50 PG per ml. And if I exponentiate that, it turns out I get an odds ratio of 0.45. So, and then I can do the same thing for IL-8, take it times 50, exponentiate that regression coefficient, and I get a odds ratio of 1.06. And so my interpretation here, that for every 50 unit increase in IL-6, the odds of infant weight being between 750 and 1,000 grams are reduced by 55%, fairly huge change. And then for every 50 unit increase in IL-8, the odds of infant weight being 700 to 50 to 1,000 grams are increased by 6%. So there you can see using a categorized continuous variable like infant weight here in this case. But if I were actually to do this, I'd probably do it as a regression and use the actual birth weight that they have. But for illustration purposes here, I've categorized it to get an ordinal outcome. Okay, so I want to then finish with this little table here of the different regressions that we have, or we'll talk about linear regression, which we've gone over, where we have the equation of an outcome, and then the regression equation, alpha in this case being the constant, beta being the regression equation. The beta is a rate of change. In other words, for every 1 unit increase in the independent variable, or the x, the outcome, or the dependent variable, y, changes by the amount beta, whether that's plus or minus. And then as we just went over logistic regression, we're looking at the logit, or the of a particular outcome, the probability of an outcome, this being for a binary logistic regression. So we get an odds ratio. And then if we have more than one category for the outcome, we're still getting odds ratios. And then survival analysis, which we haven't, or maybe we went over it last year. I can't remember. Maybe we went over that last fall. But anyway, the statistic that we're interested in, which can be interpreted in the same way as the odds ratios or the rate of change for linear regression, we call it the hazard ratio, the probability of dying in a particular unit of time. So that concludes my presentation on logistic regression. As I mentioned before, the slides will be made available to those who have registered, and then the presentation itself, the folks from Georgetown will put out on YouTube, I believe. So I have just a couple minutes left. If there are any questions, or if you, I think, use the Q&A, or if you need to go do something else, you can just email me any questions that you have at my email address here. Okay, so if there are no questions, or if you want to email me questions, we will end our session for this month, and we'll see you again in March for another presentation that should be quite interesting, where we'll look at a more modern regression method. So again, thank you for your time.